Welcome to our presentation, our tutorial about automating design and verification of embedded systems using metamodeling and code generation techniques. The tutorial was created by Wolfgang Ecker, me, Rainer Findenig, Daniel Müller-Gritschneder and Wolfgang Müller. Wolfgang Ecker and I'm from Infineon Technologies. Rainer Findenig is from Intel. Daniel is from Technical University in Munich, and Wolfgang Müller is from the Heinz Nixdorf Institute in University of Paderborn. The schedule of this tutorial is parted in, let's say, 3 parts. The first part is about the motivation, technology, and terminology. Second part is about, we used 2 well-known Metamodels, the IP-XACT and the UML and SysML, to show a little bit more using example what's it all about with the metamodeling. Then normally we plan to have after this, let's say, more or less theoretical parts. Daniel will show the practical session, the tutorial about Eclipse, using the Eclipse modeling framework, loading the IP-XACT model there, and this is a step-by-step tutorial by Daniel. First of all, a little bit about the motivation of using metamodeling and code generation. So we had Infineon designers on a single task. So that means, for example, a firmware colleague writing the firmware header files of the register specification could save 95% of time by using this code generation approach, because the concept engineering is actually specifying the register layout together with the customer, the application engineers, and you have all this data available, this formal data, and if you have a formalized specification with a generator, you can directly use the concept and generate the code. So in the first project, we saw, okay, by creating the generators from scratch, cleaning up the specification data if you use them formally. So that means there was more or less no benefit, up to a little bit benefit, but if you go to the next project, the follow-up project, where you can directly reuse your tooling, your generators, the people are trained, then you gain on this single tasks up to 95%. The other one, there was a saving on about 1 person year through test file generation. So generating out of test specifications the code, the framework, for example, UVM, register packages, e-register packages, stuff like this. There was also a huge saving in 4 to 5 person years, and the saving about handling test programs. So that means if you try to formalize your test programs and try to reuse them, try to build up a test library in this metamodeling area, reusing them, then there was also a huge benefit. The Infineon designers on the complete full chip implementation saved about 60%, also 60% effort reduction and 2-month project time using this metamodeling code generation approach. So that means there was something like register RTL code generation out of the same specification, also parts of the verification, of course not the complete verification, but the structural one. Also the software team was using this firmware header file generation. Then let's say the system level team using transaction level modeling, creating virtual prototypes, they used again the same specification to generate their, let's say, system C register code and system C top-level connectivity. So with all of this, if you have, for example, also spec changes, late spec changes, you have a single source of a specification. That means all these domains which I mentioned, like design, verification, validation, firmware, software, all of them gain about it. Just there's a specification update. They will run their generators, and the code of all the different domains are updated. Then another thing was, one of our colleagues was starting to generate also, let's say, digital analog interfaces of modules. And so that means he tried to generate most of the structural data analog digital interface, the registers, the interface of the module, and also the structural description inside the module. So this was about 80% of the complete code. Of course, this metamodeling will not replace HDL, for example, because the behavioral code somehow needs to be written. So it more or less helps with all the structural codes. Of course, later on I will also introduce some kind of where we used it for behavioral using state machine models to generate then for different domains the state machines. And this was about 80% of the structural code could be generated there. Then another of the Meta case, it's a EDA tool, MetaEdit Plus. They reported to have factor 20 speed and productivity improvement using this MetaEdit metamodeling framework for software development. So let's start with scripts supporting design productivity. I think everybody of you knows, maybe have done it yourself, taking some scripting language, have a specification, running with the scripting language over the specification, generating some code. Then people like to use your tool, then it somehow was extended. It was growing, so you used some regular expressions, undocumented, and it was great, but at some point of view, it wasn't maintainable anymore. Maybe the one who created the scripting left the company, changed the department, and somebody need to take over, but it actually wasn't really possible because it was, let's say, some kind of grown spaghetti code meanwhile, and it needs to be done from scratch. So, but at least the good thing about it is that generation was used and all this, let's say, structural code or thousands of registers or wires of the top-level connectivity weren't written by hand. Yeah? And here in this tutorial, we want to exactly show how to use metamodeling to have exactly the same benefit using a specification, for example, an Excel sheet, having this metamodeling here in the middle, and then your desired code as output. And how do we do this? The first improvement here is the model view separation. So what does it mean? It's about parting, what you have done before in one script. Let's say how I called it spaghetti code. You part it into readers, writers, and the model, the API, which decouples the input side of the output side from the output side. So that means, what kind of benefit do you have here? For example, up to now, you used some kind of XML input data to generate or to use in your tool as a single source. But then, after some time, it was required to have either not XML anymore, to have Excel as a specification, or it might be that some of the data is still in the XML and some of the data is in the Excel sheet. So you have to combine them. And as you can imagine, if you have this one script, which we've shown before, it's quite difficult to extend something like this. But here it's quite easy. You have these readers filling the API, so filling the model. And so what you are doing is you don't change anything at these sides here. You just have another reader which reads your new format and puts it into the same data structure, into the same data model. Nice thing is you really can extend this reader side, but also, let's say, if you have already filled your model, so that means your model contains all your data, like the connectivity data or the register data, all the bit fields, everything what you need in your output code. So that means here the writers, which tells what will you generate, you just put another writer output plug in there, which will generate then, for example, the system C code. Then another writer which will generate the E code. Another which will generate RTL, another which will generate system Verilog, and so on. So that means you will still have the same here in the middle, the same model, but fed by different readers, and you have the possibility to define separated, like modularized writers for this. So now we want to look a little bit more at the reader side. The reader side, I think everybody of you know because somehow concept engineering, application engineering, they are always communicating with the customer. They have their own styles, their own Excel sheets. For example, Excel describing normal RTL connectivity will look completely different than the specification for the pad ring, will look different than the specification for registers. That means everybody has already his optimized style of specification to discuss it, for example, with the customer. So that means on this reader side, you have the possibility to parse. So first of all, to parse the specification data and to sort it into this API. That means the API, just for somebody who does not know what is the API doing, for example, the API provides functions like set name, get the name, add a register, add a connectivity item, this kind of stuff. So that means if you iterate over your Excel rows containing in each row a register, for example, you will also call, okay, add a register, then set the name, set the offset, and so on. For our framework, we already prepared a lot of these parsers, so that means it's a little bit like a reuse platform at Infineon. That means if somebody already have a VHDL parser created, another project can directly use this VHDL parser. So that means, I don't know, we have about 50 different formats there, and it's growing, and everybody can use them if they need it. Because we also got to know if you have this approach with the scripting, and it's only in a department, sometimes it's only in the head of one person, that means it's not really like distributed, and since it's maybe a different language, maybe it does not provide interfaces, it almost cannot be reused, this tooling. And we also want to focus here on the reuse of parts of the generation framework itself. Yeah? Not only on reuse of specification data, also on the reuse of the tooling. Yeah? The writer side, it's okay, you can iterate over your, let's say, filled API, you model, you iterate for register and register, and then, for example, if you generate firmware header file with definitions, register name and the offset, you would just, for example, use the print statement into a file or on the console or however you want to generate and output the data. For example, you can use Intel hex libraries to use it for like post-silicon verification of your config sector and stuff like this. So that means the output side just takes the model and generates the desired code which you want to generate. For example, RTL, VHDL, system Verilog, whatever you want. Yeah, you of course have to write the generator, and you know how the generator should generate. So. But what we are normally using, it's not about here, like shown here, like print statement. We are using a template engine. So, because the reason for using a template engine, it does not require that the people really have deep software knowledge. Yeah, you know, if you want to generate, for example, here this kind of VHDL entity, the RTL engineer can just take our output as an example, and then you see here, okay, you have here your different ports, okay, it's a for loop, so that means you can just iterate over it. So that means template engine takes something like this, static code like this, gets directly translated into static code, so that means you don't need to deal with complicated escaping of characters and stuff like this. Then here the entity is also static code, but here you make a so-called substitution. That means here you access your data model, your API, and depending on the specification data, it will generate the module entity name here. Then you have pragmas, for example, to have a loop, a for loop. So that means here you access again your API. You say for a port in the component.get ports, and then you print your port name, then you have a get port type and stuff like this. So that means this generator here is very, very close at the view, at the output code you want to generate. And this is the huge benefit, because we at Infineon don't try to write, or for my department, we don't try to write all generators for all Infineon, because then we would become the bottleneck. Yeah. So we want to teach the people, we want to train the people to write their generator. The other thing is, let's say, if we have to write some kind of test generator, and for example, I have no knowledge about test, I always need to call the person who wants to have this test generator, ask, okay, is this correct what I'm generating? Then this person tells me, oh no, here you have to put a semicolon, and here. And so we have a lot of communication overhead by creating this generator. And this person who exactly knows what kind of output code he wants to have, he has, with such easy possibility with template engine, this person, this RTL designer, this test engineer can very easily write a generator himself. So that means we also try to multiply the knowledge about metamodeling, that training as a designer, not thinking only in like reading the frame, reading the specification and typing it. So thinking more in this, let's say, meta level. Okay, here I have a continuous, always doing the same work. Okay, I can put a for loop in there. And of course, not everybody in a department needs to write generators, because if somebody of a department already wrote a generator fitting to the purpose, it can be used by the complete department. But our motivation is really to train verification engineers, designers. We have even trained analog colleagues to use this metamodeling to be more efficient there. So the template engine, it's quite easy. You have here this template, what you have seen before, and the template engine itself, it's a library which we linked into the writer itself, and it just renders the template and puts the output view to the output file. 5-6 years ago, Wolfgang and I, we started giving trainings to the designers, verification engineers, and so on. But we didn't really use metamodeling, so we taught them how to write this kind of stuff here, the API, by hand. So that means the designers had to learn how to implement the API, how to implement the set functions, the get functions, stuff like this. But they told us, it's very clean, very nice, we like it, but if my boss tells me in 2 weeks I need a VHDL code ready, then he cannot spend there 2 weeks programming nice APIs and having a nice framework set up. So, and then we start thinking what we could do about this. And then we came up with the idea, okay, normally if you talk about your data, if you stand at a whiteboard discussing, then what are you doing? You normally draw your pictures. So you say, okay, what kind of data do I have? I have registered data, for example. Okay, I have a module with registered data. What do I have? Okay, I have a component, and this component has registers. So, and then, okay, a register has bit fields. So that means you think in this exactly what a meta model is. You think in structuring of your data. And then we were thinking, okay, this API is so regularly. For example, you have a component, and the component has a name. So you need a set name and a get name method. You have a register. A register has an offset, has a data width, has a has bit fields, and the bit fields again has a width, data, offset, and start bit, stop bit, whatever. So that means what to do there is we read this meta model, so this drawn picture, let's say, we read it again in our tool framework API, and then we generate this API. And what else do? We also generate a reader for XML, which will automatically read the XML file, which corresponds exactly to this meta model, to our data structure. It reads the XML data into the API, and we also generate out of this description a writer, which is able to use the data of the model and generate again an XML file. So that means, okay, just draw your picture, your meta model, your diagram, press a button, and you get most of the parts of the framework generated. Yeah? So that means, okay, we don't give the people, you know this with the, I always use it in the training for the colleagues at Infineon. There was this, somebody is walking in the forest and sees somebody sawing a tree, but he is not going through because the saw is very rusty, very not sharp enough. So, and the person who was walking by asked, why are you not sharpening the saw? And the guy said, no, I don't have time to sharpen it because I have to saw. Yeah, and this is mostly in like all of the projects that people have deadlines, people need to finish their work, and if we, for example, from the central department doing some new fancy methodologies, telling them, can you use it? And they say, no, I have to work here and get my job done. And that's why with this approach that they can directly generate this API, most parts of this generation framework which they will use, we got a lot of, let's say, customers in the company using this framework. It's again, as I said, this API generator works in exactly the same way like all of our generation frameworks. We have a reader, for example, in UML, I will come to this later. We paint these diagrams, we paint these meta models. Then in a UML tool, for example, you can save your meta model as a XMI, so like a XML-based file. You have a reader, or we have a reader here, read it in our created API, and then here as a writer, we output the desired readers, writers API code. Exactly. And at our framework, I think I forgot to tell it, we are using mostly Python to do all of this. Daniel will later on present this Eclipse modeling framework. It's more or less exactly the same what we are presenting here, but when it comes to Java, so let's say a non-scripting language, it's difficult sometimes to persuade the RTL designers to dig more into this software know-how. So that's why we currently stick to the Python, because it's also quite extendable. You can link C++ into it. You can connect it with Java. And yeah, but we are also digging more in direction Eclipse, let's say GUI extension for all this meta modeling. So this slide, this aspect here is quite important. Automation of your tooling. So the core model, for example, in our case, this one here is our core model of our framework, of our tooling. So our tooling is called MetaGen. It's proprietary and developed in Infineon. But a core model in general has the possibility to have untyped, typed attributes, to have children like compositions, to have links like linking between elements. You have possibility to specify constraints like the multiplicity. For example, if you say, my module always need to have a register, but if it does not have a register, it will automatically output a warning. Other constraints might be, okay, you have a bit field, and this bit field has a width of 1, but you specified a constant, a enumeration with a width of 2, obviously this is a semantic error and you have to output an error. So that means you always have some kind also of pre-validation of your specification data. You clean up your specification data. You don't need to go to, let's say, VHDL compilation, simulation, synthesis. You can upfront do a lot of semantic checks, so in an early state. There are metamodels like the XML with the XSD schema. The XSD schema also describes how should the XML look like. Then what we see in the next presentation will be the UML, which is based on the MOF model. So MOF is the Meta Object Facility. And this Meta Object Facility, the eMOF is the essential Meta Object Facility because this UML is very, very, very big. And this essential Meta Object Facility is compatible also to the EMF Eclipse modeling framework, which will be presented by Daniel in the tutorial, with its eCore model. So that means the eMOF and the eCore, they are compatible to each other. And as I already mentioned, the MetaGen here, based on this MMAnalyze, is the thing we developed at Infineon, what we are using for metamodeling, code generation, and all this methodology. What we will see in the next slides also is first how to do this data modeling, what is the thinking behind it, and we will go from the meta model to the meta model. So this is also shown how this belongs together. When you think about meta modeling technology, modeling is about structuring and formalizing things. So that means you want to really, you register specification formalize. Or you have something like this, okay? Something completely different because it's not all about like registers which are covered by, for example, IP-XACT or top level or design code. It's about formalizing all kind of specification data. Even, for example, for your own resource, you could do something. You can formalize everything. So here, for example, we have some kind of car. The car has some attributes, some properties, like the type, the name. Then the car has wheels. A wheel has a position, yeah, and a type. How big is the wheel? Then what are the pressure sensors? The pressure sensors, who is the provider? And what is the chip which is provided, for example, for this pressure sensor? Or you have here electronics with the version, voltage, whatever specification data you can imagine. And as I also said it as this example for register specification, here you would say you have a component has registers, and registers have bit fields, and bit fields have constants, for example. Yeah, then you can say, okay, also your module have interfaces and ports, and how are interfaces related to registers. This you can all express with this meta modeling, or let's say modeling and structuring, formalizing things. How does it look like in a meta model? Because this one here is the model. This is the structured model. But what is a meta modeling doing? A meta model is structuring the model. So before we've seen a model is structuring the data. And here's our model, but the meta model is structuring our model. So what do we say, for example, here? We have here a car. This is one time there. It has a type, and this type attribute, what is it? It's a string. It's not an integer, it's a string. So the name is also a string. Then we have the possibility to say, okay, is it an optional attribute, or is it an attribute which needs to be there? Otherwise, it's not possible, for example, to generate valid code because the essential attribute is missing. Yeah? Then here, 1 to star, we say a car needs to have at least one wheel. If the wheel is not specified for a car, we have an error. That's why you have here this multiplicity constraint, which says, okay, we need 1 to star wheels. Better, of course, it would be you have 4 wheels for a car, but maybe it's a different car. Maybe it's a car with 6 wheels. Who knows? Yeah? Then the position would be an enumeration type, because an enumeration would say, okay, the position might be left, right, back, and front, or something like this. Yeah? Provider can be a string, and like this, you just tell, how is my data structure? So how should be my model structured? This is the Metamodel. Here we've seen what is the thing. This would be an attribute like a primitive attribute, an integer, a boolean, a float, enumeration. Then you have here your multiplicity constraints. You have here your compositions. So that means how many objects do you have here, like a list of objects. Here multiplicity is 1. A wheel has only 1 pressure sensor. And like this, you can upfront, when you're structuring your desired data, you can already say, okay, what are the basic constraints of my model? Yeah? So that you don't need to write yourself checker which checks the model. So there's also UML and IP-XACT. So these will be like after the introduction. This will be detailed view on what is UML, what is IP-XACT. So UML is a graphical formalism to describe software systems. So it can describe structure, behavior, and interactions of behavior and structure. For example, you have class diagrams, object diagrams, activity diagrams, and I mentioned already the state diagrams. So UML does define a lot of different models already. Then I already mentioned this meta-object facility as a core model UML is based on. And the essential meta-object facility, which is like a subset, which is compatible to the eCore model of the Eclipse modeling framework. And there are already languages defined like the object constraint language, where you can formalize checks on your model. Like, for example, okay, a register name is only allowed to be 9 characters long. A bit field offset plus width should not be greater as the data width of the register. Stuff like this can be formalized in this object constraint language. Then we have stereotypes UML profiles. That means it's already like extended UML, like the SysML and UML Mate, which is some kind of UML profiles which support the modeling of embedded systems. IP-XACT, most of you heard about IP-XACT. It defines the, let's say, data core models for specification reuse, exchange. For example, it defines how our registers are structured, how is top-level connectivity structured, how is transaction-level modeling connectivity structured, how are interfaces structured, and it's like an industry standard, and you can, if you have IP-XACT models and you are an IP provider and you want to provide your IP, you deliver also an IP-XACT file, and then the customer can easily integrate your file in his system. Yeah? So we will see Daniel will give a detailed presentation of this IP-XACT model. Second part of the tutorial. Okay, the thing is, which is very, very important, because I think this is also the reason why EDA has sometimes their difficulties to provide all the different flavors which a company needs. For example, if you have sensors, transistors, power, analog, a lot of different, for example, Infineon has automotive, let's say the safety requirements. Then we have also security, like chip card, to have the security standards. So that means it's almost impossible to have one generator covering all the needs of Infineon. It's impossible. So that means it starts with firmware header files. If you have a different CPU architecture, you need different firmware header files. So that means I think I've seen already 10 different firmware header file generators and styles to fit the needs of the specific projects. That's why this meta modeling is very, very important, because you need to be flexible. You need to be flexible and you need to adapt to the requirements of your designs. Yeah? First, extendability is required, constraints are required, interaction and compositions. Examples for this, I already gave some, but for example, analog types and their properties. If you want to do analog and digital modeling and you have mixed signal system, let's say, and that means you have to deal with analog types in your digital design environment. What are the requirements? For example, some of the projects want to still be able, after synthesis, to simulate analog detailed. That means you need some kind of special analog types. Other projects, they are pure digital, they don't care about all of this. So that means somehow you need to deal with this. Then register protection and mechanisms. You have so many different bus systems and different projects fitting to the need of the projects, and each bus system, each CPU system have different protection modes. So you have some kind of end init signal, yeah, and the register is physically writable, but is only physically writable if the end init signal is 1, for example. In another register, there need to be a specific value that another register is writable. So you have so many different cases that it's again impossible to write a general purpose generator. That means with metamodeling, it's quite nice because the metadata is still the same for all projects, maybe with a little bit more extended information, and the specific generators for the projects, with the knowledge of the projects, they can output the desired data. Or here you have, maybe for TLM, you have event-based state machines. You want to have a system C event-based state machine output. But for RTL, you have a clock and state diagrams. There are already some of the models supporting this. For example, inheritance. With inheritance, you can extend your models. Or with this UML profiles or this object constraint language, it's possible to fulfill constraint requirements. And also XML provides, so the XSD schema already provides some constraints on the data types. Yeah, so that means there is already something out there, but with metamodeling, you've seen you can define whatever metamodel, whatever model you want to have. It's always possible to define the model for your needs. Here we see, for example, that we have 2 frameworks. Yeah, so it might be that your top-level specification data is not optimal structured for the output, for the generation output. So what could you do? You have your specification meter model, you generate your framework. Then you have your generation meter model, you generate your framework. And here you have a translation of this model to this model, and then your generators use this model. So that means you have a possibility of combination different toolings. For example, I told we have this reuse platform. So that means even complete frameworks which are created by the colleagues, they can be again reused in a bigger framework to have this extension and reuse possibility. Yeah. There is also, for example, linking different models. There's also this XPath mechanism in place if it comes to XML, or you can define the semantics for your own interlinking mechanism. So that means combination, reuse, building blocks, like I don't know, Lego, you build your bigger systems out of smaller systems. So now we've seen a lot of like model and view and output, and how is it everything like layered. This is the layer structure for the metamodeling, so it comes also from the UML definition. I like to start with the view because normally you think in I need VHDL entity, I need firmware header file. So that means the view is the output of the data, the view which you need for your design. Then the model is like the data, like the register data, for example, the register name, the offset, and so on. This is the model. The meta model, again, is the definition. Just, okay, I have component with models. And what is meta modeling? A meta model describes the meta model. Yeah? Here in the meta model, you describe your model. But in the meta model, you describe your model. We have the possibility, so we try to always generate more. So we started not only to generate our modeling and generation framework, we already started to generate the framework which will generate the desired code. So to have more automation in our tooling. This is the layering. So, and here we have an example. So for example, IP-XACT. IP-XACT is a XSD. A XSD is a meta model. So it describes how is the IP-XACT model structured. So what do we have here? We have here a XSD meta model, which can read all different XSD descriptions for IP-XACT, for all other XSD specification, HTML, whatsoever. We read it in, and then we have the data of the XSD meta model filled. Then we have a generator which will generate the framework out of it. So that means it will generate for IP-XACT XML file the reader, it will generate for a XML file the writer, and the API for a XML file. So if we use now a XSD schema of something else, then we can directly read this, just press a button from the point here, and we will get all this generation framework generated. So this is about the meta modeling. The Eclipse modeling framework is able to do the same thing, so Daniel will present it later on. And important to know is that the meta modeling approach or technique or methodology is not a new thing. It's there since more than 25 years. Yeah? So formerly it was called the Express Information Model. Then this Express Information Model was further developed by the CFI, the Common Framework Initiative. And then there was the formal foundation for this EDIF. Yeah, there's also a book about meta modeling. Sorry, I don't know the date when it came up, but all this kind of thinking is already more than 25 years old and mainly used for software development. So as a summary, meta modeling and code generation is an industry-proven technology to efficiently build domain-specific tools for a specific structure. So you've seen you have possibility to define your meta model and generate whatever output code, whatever view, whatever the domain-specific tool you want to have. Modeling in the context of meta modeling is structuring the design content, yeah, for example, your specification data. And meta modeling is about structuring the models. And the thing is, try to automate whatever is possible to automate. And we are also going the approach because some things are very, very difficult to automate. So that means we also say, okay, this is so difficult to automate, we don't do it now, but we automate the other 80%, which is like low-hanging fruit. We do this, and maybe later on, if there's a positive time or if there's some kind of benefit, then we also automate the rest. But if not everything is automated, then just some pieces are written by hand, but at least most of this code, most of this, let's say, not lazy, but this typing code, yeah, of thousands of registers is automated. This UML presentation right now, it was done by Rainer Findenig from Intel. We were, before the split with Infineon and XMC, we were colleagues, and he was doing a lot of UML modeling in his PhD. specialty using state machines. So, and this is about UML, how to extend it, and to give an example, how to use UML to specify, for example, state machines. UML, from Wikipedia here, the Unified Modeling Language, UML, is a general purpose modeling language in the field of software engineering, which is designed to provide a standard way to visualize the design of a system. So, to interpret this, what does it mean? Okay, UML was developed and used mainly in the field of the software engineering. Then, important, try to find a standard way to describe objects. So this is the OMG, the Object Management Group, which defined this as a standard. And UML tries to be a graphical system to specify your data. So, as we've already seen for the metamodeling, the class diagram, here you have your classes like registers or SP5 frames, whatever you want, or for example like states or state transitions. So here you can specify your class structure, then there's a component diagram, deployment diagrams. There are a lot of structural diagrams defined. And you have the behavioral diagrams, for example, an activity diagram, sequence diagram to specify how interactions are taking place, the state diagram. Very important also here, a focus of this presentation is how to model states, how to model composite states, concurrency for states, events, and so on. This was just an idea about what is UML describing, structural and behavioral modeling. Here, for example for the UML state diagrams. Yeah? You have, for example, here your initial state of the state 1 here. So initial state goes into the state 1. Then you have transitions, so going from one state to another state. There's the possibility to have composite states. So, for example, you have here this state and this state, which are running concurrent. Yeah? And you have here finite states leaving the composite state here to the states 3. So that means you have possibilities to graphically specify your state machines in UML. Very important is it's a graphical language. Yeah, it's easy to read. Yeah, you have seen if you have here this quite small state machine, it's easy to read. But you can imagine if it becomes more and more complex, then sometimes a graphical representation is not so beneficial. That's why easy to write, you have to think about how to structure your composite states and how to fit everything that it's still readable. The semantics of UML, they are not formally defined, so it's textual written, and you have to think about how to read, how to interpret this semantics, maybe to have your own semantics which are specific for your project, and then you will integrate. So you have, for example, the standard, you have your state machine, but the generator which will generate the output, for example, the VHDL state machines or the C state machines or the system C state machines, they will follow the semantic you will code in your generator. So that means you have to think about formalizing the semantics in your generator. And that's why, of course, tool support is quite critical here, because if it does not fit your semantic or the semantic was not correctly interpreted, it might be a problem. Integrating the semantics in your generator. So this is, of course, very, very important, because let's say if you have already implemented generator you cannot change, and this generator does not exactly generate what you need, then you have a problem. But with this approach that you create your own generators, it's very easy to adapt it really to the needs of your project. If you create your own generator, you have the possibility to adapt to each need. Next thing is UML exactly maps. It's exactly the same layers which I introduced for the metamodeling before. You have here the view, what should be the output. Then the model, it's the M1 layer, the metamodel, which is the structure of your model, and the meta model. So in this case, the MOF, so the meta object facility of UML would be the meta model for UML. Output view, the model, meta model, and meta model. Same as we saw before. So there's a possibility to extend the standard, the UML standard, to extend it to your needs. So there's also quite good tool support for this so-called UML profiles. So that means you have here the meta classes, for example, a state. And if you want to define your own, let's say, stereotype, your own state, like initial state, you can inherit from the existing state and implement your user-defined state. Or you have here UML state diagram defines a transition, and you can define here your clock transition, creating the so-called stereotypes. And the collection of your stereotypes is the UML profile. Then there's a possibility to extend even the meta object facility. That means here on layer 3, you remember the meta model can be extended by, let's say, really rewriting new states, new transitions, new regions, everything to create new. So for this approach here, there's not so good tooling support directly integrated. Then for the late byte possibility for profiles. Then SysML is a very, very known UML profile for embedded system modeling. It is an extended subset of UML, and it's using this UML profiles. So for example, you have your SysML diagram. It was extended. You've seen the blue ones are completely like new created classes, like the requirement diagram or the parametric diagram. Then the white ones here are directly used as is from UML. And the green ones, they are extended UML. So that means you've seen you have here a block diagram, but you don't have a class diagram. So that means they extended the class diagram for a block diagram and use this, for example, here to specify the blocks of their system. For example, you have a memory, you have some peripherals, the bus arbiter, bus master. Here you have your bus system. So you can, in UML, using the SysML profile, you can create your system. And here I have to say, this is exactly what I meant before with the drawing and the graphical representation. If you think about a system which has, 500 PET instances and 6 CPU systems, hundreds of instances, and you want to graphically somehow connect them, then I think this approach is limited. So here, let's have a closer look at the bus system. You have here, again, the bus master. You can define your interfaces, master interfaces, the bus port, arbiter ports, and you can connect your system using exactly this profile. That's SysML about. Then Rainer, in his, I think, also PhD thesis, and for his needs, he made also a UML profile because he was doing like state machines, not clocked state machines. He developed this event-driven state machines, and that's why he needed to extend the transitions to an event transition, and he needs to extend it to a clocked transition. So either if he's modeling state machines for TLM or if he's modeling state machines for RTL. So, and as I said, this tool support and UML tools already provide that you can even define other like representation of your extended diagrams. Here, for example, for the event-driven state machines, he extended the initial state because it was required that he has a state, the properties of a state to be an initial state and not just an initial state. So then he needed for his work global variables, local variables. So globally for all the states, locally only for some specific states. He was working also a lot of abstraction levels, as I said, transaction level event-driven state machines and clocked state machines. If you have a top-down approach and you first create the transaction level ones, so the abstract ones, you don't want to throw it away. You want to have a mechanism to reuse, to have like a refinement from TLM to RTL and the other way around. How to cover this? This is covered by having an abstract definition, and the refined one will inherit from the abstract one. So we will see a small example for this, how it works. Let's forget first about the right part here. The left part is just you have a serial interface like a TXT state machine. Yeah, you receive data, somebody writes data from the core, from the CPU to your transmit register, then the state machine is triggered and you want to write the data to the output. So that means you have here the initial state, it changed to the sending change state. Here it iterates as an activity, it iterates over the data and sends it to the output, like event-driven with transaction level modeling, and returns again to the idle state. Yeah, this would be more or less the abstract one. And now you want to define, okay, like with a refinement, you want to have here your clocked sending, not just the sending, the clock sending. That means you inherit from this state, and then you have here if the start bit is there, if the data bit is there, the stop bit is there, and then you leave it again. And in the clocked mode, this composite state is exactly at this position instead of the transaction level one. So that means here again with the semantics, because if there is not something out in the design world in the EDA which has event-based state machines for your need, which can be extended to clock-based, you have to somehow have, for example, your metamodel. You read this XML in your metamodel, and you have your generators to generate, for example, RTL code in case of this, and TLM code in case of this. You can also extend it then for software, for C modeling, for your C drivers, for example. Then you can also have your own generator for this, exactly fitting the needs of your CPU architecture and so on.
This presentation was done together with Wolfgang Müller from Paderborn and just covers the kind basics of IP-XACT. So IP-XACT is industrial standard. It's standardized by IEEE. Basically what it is it kind of replaces the document. If you get, for example, some IP, VHDL files, Verilog files, and then instead of getting a big PDF document, you get this IP-XACT. And it's kind of a machine-readable format which describes the interfaces of this IP, which describes the register interfaces and so on. And this can then be interpreted by your integration tool. And it has some history already. So in 2003. At the moment, we are at the version 1.5 or IEEE 1685 2014. And related to that, of course, is also this system RDL language, which is a mere focused really on the registers. While IEEE has a little bit of a broader scope, as we will see. In general, if you get IP-XACT files, they are in XML files. So just have a short thing what XML is. And the way these XML files are written is defined in a so-called XML schema. So there exists an XML schema for IP-XACT, which you can just download from the Accelera website. So XML, if you're, for example, familiar with HTML, it looks very similar. You have these tags. For example, here we have a tag program. And for this program, we have some subtags, which are the language, the file name, and some source information. So that would be an XML file. So this is a filled out model. And the XML schema, in contrast, then kind of describes us how to write such a XML file. So this XML file has a special format, and this format is defined in the XML schema. So in the XML schema, you say you have an element, which is the element program, and then inside the element is described what is the type of this element. So it's a complex type, and it is actually a sequence which has the field's name, the one field which name is language, one field which name is file, one field which name is source. Here actually the type doesn't have a name. This is called an anonymous type. We will later see actually that also IP-XACT makes use of these anonymous types. We have to consider that when we write our generators later on. Okay, let's go back. That's kind of this metamodeling environment we are looking for. So in this case, we have the XSD schema of IP-XACT, which we can use to generate our API. And then we get a design environment for IP-XACT. We can read in IP-XACT models, and then we want to generate some design and verification code. There exist some simple editors for XML, but that's kind of a very manual task if you want to try and go really in and modify these XML files to your needs. So it's much better actually to go and take some advanced IDE tools like the Eclipse modeling framework, as we will show later on. That's basically the IP-XACT IEEE standard, how it's built up, and I will now go a little bit into details on interface definitions, components, design, abstractor, and so on. So let's take, just to begin with, one example, the so-called component instance. So the component instance is inside a design, you want to instantiate a component. And here you can see it's the same way it's structured. It should have an instance name, which is of type name, and it has a display name, which is of type string. So the difference between is that, for example, if you have a name type, you have to have an individual name for each component. So this is an individual identifier. You can for sure identify your instance. While, for example, if you have some IP-XACT design environment, you could also choose some other display name, and then two components could have the same name. You get a description, then you have kind of a Boolean value which says if this thing is actually there, and then basically this will also be something we will look later on with more detail. You just get a reference on the component. And finally also there are some vendor extensions, so there's actually a way to extend IP-XACT in a way to stay still within the standard. So there is actually a standard conform way to extend IP-XACT to your needs. For the big picture, we get some design environment, then we get our component IP, which are the VHDL files, then we have some IP we might need to connect components from different abstraction levels, some simulations models and so on, and then we get a lot of data which is then formatted in IP-XACT, and these are all these XML files. These are taken actually to describe your system or your IP library, and on the other side you can also have some XML information in IP-XACT which you need to generate your design and verification code. So you can also give some additional encode in IP-XACT some additional information on how you want to generate design and verification code. So for the IP-XACT objects, the design basically is like a top-level connectivity, top-level netlist. The component, this is kind of the essential part, this basically describes what interfaces your IP component has. Can be ports, can be bus interfaces, can be the address space, memory maps, registers, parameters, different views, and so on. And here also, for the bus interface is actually described by having a reference on a bus definition and on an abstraction definition. The bus definition basically describes what protocol is supported with this bus interface, and the abstraction definition then gives the details on how this bus interface is implemented on the abstraction layer you want to look at, especially RTL, TLM, and so on. And in order to find that, so the bus interface actually, to reference such a bus definition, it uses the vendor library name version reference. So all objects in IP-XACT are actually identified over this VLNV identifier, which is very unique to IP-XACT. And this is also something we have to consider later on when we are writing our API for our model. So this is an example. For example, we have a design, which is a top-level connectivity. It has an instance of the component C1, and then it has an instance of a hierarchical component. So a hierarchical component can then include, again, a design, and the design has some other connectivity. This is an example taken from, this is an open source IP-XACT tool, and here you can see an example how such a top-level connectivity could be looked, or how it could be represented graphically. So it has a graphical GUI, and here you can actually see the component instance description for this serial interface. It has instance name, so SIF0, and then it has this component reference. So it references to the component where this, to the component description. Now, if we look into the component description, we have, of course, first a description on versioning and the encoding of this XML file. Then we have the schema information that we are using the schema from Accelera, which is the Spirit 1.5 IP-XACT. Then it gives you the unique VLNV identification. And here we have bus interfaces, we have the views, and you can also define some extra ports. Also, if you have some ports which are not part of the bus interfaces, you can also define them for each view here in the component description. If you take a deeper look into the bus interfaces, then we have the bus, this is the name here, SBI, and then we have a reference to the bus type, which is a VLNV identification, and we have a reference to the abstraction type, which is again VLNV. And then we can have some additional configuration. So for example, this one is a slave interface. The same thing is here, for example, some additional ports. Yeah? So behind the bus interfaces, we have some additional ports. In this case, there should be some clock. Yeah, here you can see. So the clock actually is defined as an additional port of, with 0 or 1, and is type standard logic. Then we have some additional objects. So the abstractor basically is something you can put in, for example, if you want to provide also some simulation models with your IP, that you then also have kind of IP which connects them together. The catalog actually is used because the VLNV, and basically to map the VLNVs to the files. So each component is then basically in a different XML file, and so that you can come from the VLNV to your file name, you have to then basically query the catalog. And then you can also give some additional information, configuration data on your design. So going back to the big picture, now we have seen here basically what kind of information we are using. Let's take a look at the right side. Where the generator can then process these things. And the standard actually says that you should connect these generators via the tight generation interface to your design environment. This basically, this TGI is a HTTP-based protocol where you can query for different XML data.